Hello, my name is Alicia Lanz, and I am a postdoctoral fellow at the Carnegie Observatories. I'm here today to tell you about a new instrument concept, the Magellan Infrared Multi-Object Spectrograph, or MIRMOS. Most of our understanding of galaxy evolution has been built upon large galaxy surveys that, for the most part, have been carried out in the optical. In the last decade, new near-infrared multi-object spectrographs have enabled the first statistical views of distant galaxies in their rest optical reference frames, but the sample sizes of these near-infrared surveys are considerably smaller than what has been achieved in the optical. Some of this exciting science facilitated by the near-infrared spectrographs includes galaxy redshifts, quasars at the epoch of reionization, stellar populations, dust maps, active galactic nuclei, chemical abundances, and cosmology, much of which has been discussed at this conference today. Dust in the infrared is especially photogenic, as shown in this near-infrared image of the very dusty North American nebulae that combines data taken by Spitzer's infrared array camera at infrared wavelengths. Here we see many state-of-the-art near-infrared spectrographs, with which many of you are familiar and probably have used for your research. Such spectrographs can be broadly divided into two categories. In the yellow, you can see the single object near-infrared spectrographs, which are characterized by a limited field of view, but a much broader range of near-infrared wavelength coverage. In contrast, in the orange, we have the workhorse multi-object spectrographs, which often have a wider field of view that allows for observation of multiple objects simultaneously, but generally has narrow wavelength regions. While these instruments have been very important, each class of instrument has limitations. Specifically, the single object spectrographs have a very small field of view, while the multiple object spectrographs have the narrow wavelength coverage, and most often you can only observe in a single band at a time, which of course provides limitations if you're trying to characterize multiple bands of an object, since often the data is taken over time where the atmosphere changes in between, or so you can't compare the data you received in different bands very well. Because of these limitations, galactic and extragalactic astronomy is really ready for the next generation of infrared spectrographs that combines the strengths of each of these classes of spectrographs and results in a new instrument that has a larger field of view and multiplexing capabilities, that has the larger field of view and the multiplexing capabilities of the multi-object spectrographs, and it takes those and combines them with the broad wavelength coverage of single object spectrographs. We are designing this next generation spectrograph, the Magellan Infrared Multi-Object Spectrograph, or MIRMOS. It has a larger field of view of 13 arc minutes by 3 arc minutes, which can be utilized by up to 100 slit positions, simultaneously observed in 4 band passes between 0.89 microns and 2.4 microns, the Y, J, H, and K bands. The MIRMOS field of view is shown here on the left in comparison to the moon and to the MOSFIRE field of view. All four MIRMOS fields of view, all 4 MIRMOS bands are shown to represent each wavelength bands, the yellow, brown, orange, and red. The total wavelength coverage of MIRMOS is shown on the right with the associated expected transmission for each band of the spectrograph. In red, you can see the Y, J, H, and K labels. MIRMOS is driven by its science requirements, which are set by a specific set of science cases. MIRMOS will map the topology of late reionization by detecting Lyman alpha and metal line emission from galaxies with redshifts greater than 6.5. MIRMOS will delineate the connection between galaxies and the cosmic web by measuring galaxy properties in large-scale environments at cosmic noon. MIRMOS will track gas flows in and out of galaxies by imaging the circumgalactic medium in rest frame optical emission lines, shown here. MIRMOS will characterize sources discovered in next generation wide area surveys. MIRMOS will survey the molecular content of exoplanet atmospheres by achieving very high spectrophotometric precision. These science cases lead us to a design for a spectrograph with simultaneous wavelength coverage of the Y, J, H, and K bands and a spectral resolution of R of about 3,700. Seen here on the bottom left is a mechanical model of MIRMOS. The cryostat is shown in blue, and light enters from the extended snout of the instrument that's in the upper right of the bottom left image. The light then travels through the configurable slit unit, which you can see in a little bit of red, and then it is split into 4 arms or channels, shown here in the blue optical layout that's in the upper right. Note that that optical layout is reversed from the light path in the Dewar, where the long incoming component corresponds to going through the snout and the CSU. You'll also note that this light path has a 5th arm or channel, which is the I-band channel used for CCD imaging. The simultaneous wavelength coverage of the 4 channels is created using dichroic filters, which are widely used in the optical, but are rarely employed in the infrared. Additionally, to get the wide field of view and the larger slit length, Miramax uses fast f1.5 cameras that I will be designing and building. These cameras, one for each channel, also contain a volume phase holographic grating, which are low scatter and minimize contributions to the interline background. A solid model of one such camera can be seen in the bottom right. So after passing through a dichroic filter, the light travels through that VPH grating and along the additional optical components until it's recorded by the H2RG detector at the end. Miramax's multiplexing capability is provided by a cryogenic slit unit, or CSU, that acts as a configurable spectrograph mass. The robotic CSU comes from the Mossfire lineage and consists of pairs of moving opposing bars with slits bonded at the end. Masks can be formed with just under 100 targets across the 13×3 arc-minute field of view. And you can also form masks with independent or different slit widths. You can form really long slits, or you can fully retract the bars entirely. The left image shows a side view of a single slit. The bars are in pink, and they're extended equally across the field of view to meet in the middle. The rectangular units around those bars are the things that control the motion of each bar individually. On the right, you can see an isometric view of the full configurable slit unit, with half of the bars extended on the left side of the image, and then most of the bars on the right side removed to make an interesting looking image with just a single bar left at the back end. Miramax has an additional novel component, an integral field unit, or IFU, which enables spatially resolved spectroscopy sampled with 1 arc-second image slices. The image slicer shown here is actually from the Muse instrument, but it's produced by Winlight Corporation, which is the same vendor that Miramax plans to use. And you can see the 4 identical stacks of 12 slices of the slicer, which cut the entrance field of view into narrow, thin strips. And then the light beam is then redirected into slightly different directions, resulting in final images at slightly different places fanned out. The IFU on Miramax will be the largest infrared field of view IFU at 26 by 20 arc seconds. This is well suited to those CGM emission regions as well as other science cases. Miramax has transformative potential for extragalactic surveys. The broad wavelength coverage and the multiplexing allow for multiple challenging programs to be carried out simultaneously. Here, we have proposed a 45-night survey with Miramax that will result in world-class data sets from cosmic noon to epoch of reionization. The data there include typical star-forming galaxies, including spectral coverage of all strong emission lines, quiescent galaxies with sufficient signal-to-noise spectroscopy to characterize their stellar absorption features, shown in yellow, and reionization epoch galaxies, including simultaneous constraints on Lyman alpha and other UV emission lines, shown in pink. All of that science can be extracted from that single field of view shown in the bottom right-hand corner. To conclude, the Magellan infrared multi-object spectrograph has a large field of view, multiplexing capability, and simultaneous wavelength coverage of Y, J, H, and K bands, leading to a factor of 5 increase in survey speed over existing galaxy surveys, which will lead to transformative science. Miramax will achieve first light in 2025. Thank you for your time.